Thank you. Welcome. This is work that was done in collaboration with my wonderful collaborators Christopher Liebchen, Andre Humescu, Luca Stavi, Per Larsen, Ahmad Reza Sadeghi, Stefan Bruntaler, and Michael Franz, both from TU Darmstadt and UC Irvine, my institution. So first of all, why do we need to listen to another talk on code randomization, targeting, defending against code reuse attacks? Well, it turns out that the existing solutions don't entirely meet the goals that we set out for this project. We, of course, want something that is secure. We want to prevent code reuse attacks, such as the return-oriented programming attack or jump-oriented programming. However, we also want to prevent state-of-the-art ROP attacks using memory disclosure, such as the JIT ROP attack from 2 years ago. These attacks allow the attacker to arbitrarily disclose memory after it has been randomized, and thus bypass most existing code randomization. We also want a system that is comprehensive. We want to protect the entire application, both all ahead-of-time compiled code as well as any dynamically generated code. We want to protect real browsers. These memory disclosure attacks target browsers primarily, where we have a scripting context. And thus, we want something that can protect a real-world, state-of-the-art browser that you all use. And of course, we want something that is fast. No one's going to use our techniques unless they're fast enough. So just a little bit of background on the assumptions that we make. We assume that there's a couple defenses in place that are widely used in practice. First of all, we assume that we have DEP, or writable XOR executable memory. This prevents the attacker from injecting malicious code into the program address space to run his code. Second, we assume that ASLR is in place. ASLR maps each program segment at a randomized base offset. But as we'll see in a few moments, this is by no means enough to prevent code reuse attacks. Secondly, we assume a very advanced attacker model. We assume an attack model where the attacker can disclose and read any readable memory in the program address space. The attacker can write to any data locations that are writable by the program. And we assume that the attacker has the ability to perform arbitrary computation on the target. For example, with JavaScript in the browser context. So let's give a brief history of how have memory disclosure attacks and code reuse attacks evolved. First of all, to bypass ASLR, attackers started disclosing a single code pointer. So since ASLR only randomizes the base address of the program, the attacker needs to disclose a single code pointer into the program and then can relocate the return-oriented programming attack to adjust for this randomized base offset. We can prevent this, and it's been proposed in many different works, by using fine-grained randomization. So the problem with ASLR is it's randomizing at a very coarse-grained granularity, the entire program code segment. If we instead randomize at a finer granularity, say function or basic block or even the instruction level, we can prevent disclosure of a single pointer from bypassing our defenses. Well, to mitigate or to get around this defense, Snow et al. Proposed JIT ROP, which uses what we term direct code disclosure. The attack reads the application code after it has been randomized, and then builds a ROP attack on the fly to target this specifically randomized version. Turns out that there's a very nice conceptual way to prevent this: prevent reads to code pages. Normally, the program doesn't need to read its own code. And so if we can enforce execute-only memory, we can prevent a JIT ROP style memory disclosure where the attacker discloses the code pages directly. However, this isn't the end of the story. There's still code pointers in readable data that point into this execute-only memory. So even if we have execute-only memory, the attacker can still derive some information about the code layout that has been randomized. We call this the indirect code disclosure, and it was shown in the isomerin, the attack style part of isomerin from NDSS this year. I'll talk a little bit more about indirect code disclosure in a moment, as well as our novel defense against indirect code disclosure, which we term code pointer hiding. Briefly, we transform code pointers to make them opaque to the attacker, so the attacker gains no knowledge of the real program layout from code pointers. To summarize, we have two types of memory disclosure we want to prevent: direct code disclosure, where we read the code pages directly, and indirect code disclosure, where the attacker gains some knowledge about the code layout from readable code pointers. First, how do we prevent direct code disclosure? As I said, execute-only memory does a great job of this. There's been 2 previous implementations, but they don't entirely meet our goals, so we have a new system to fully enforce execute-only memory permissions on current state-of-the-art x86 hardware. To do this, we need to back up a little bit and look at how virtual addresses are protected and translated to physical memory addresses. This is normally done through the page table. In x86, we have a page table that translates virtual addresses to physical addresses and implements memory protections. So we can implement the non-executable protection so that data pages are not executable. However, on Intel, execute implies a read permission. So we can't have separate control over read and execute so that we get execute-only memory that is not readable. However, taking a closer look into the Intel manual, we discovered that a virtualization extension, the extended page tables, actually allows us to independently control the read bit for a page and the execute bit. It turns out that they implemented this as part of the VMX extensions, and what the processor enforces in hardware for memory pages is actually the intersection of the page table permissions and the extended page table permissions. Thus, by setting the execute flag in the extended page table and not the read flag, we can get these green code pages that the attacker is able to execute but cannot read. This is what we want. We want the program to be able to execute its own code. We don't want the program to be able to read its own code. We don't modify data pages at all. They're simply left read-write as normal. So on to the second type of memory disclosure, the indirect disclosure attack. Now, why is this dangerous? So the attacker can read code pointers that are located in readable memory. Now, let's assume that we have a somewhat medium-ish grained randomization. Let's say we permute the order of functions in the program. This is a very efficient way. We can also permute the order of pages so that we get memory sharing still. This has been demonstrated previously. But it means that the indirect disclosure attack is actually very malicious. What the attacker can do is, by reading code pointers into these functions, he can then disclose the contents of individual functions. Since we don't randomize inside the function, the attacker can then reuse any gadgets inside a function that he has a code pointer to. As the co-op attack from just before showed, there's lots of code pointers sitting around in data that the attacker can read. So we need to protect these code pointers from giving the attacker access to the gadget locations inside these functions that we randomized. We do this with a technique we call code pointer hiding. Now, we reached into the bag of computer science tricks and pulled out add a layer of indirection. We simply rewrite all code pointers that point to executable pages through what we call trampolines. Now, these trampolines are simply direct jumps to the original destination. So we can take function pointers and point them to a trampoline that then jumps to the original function. We take return addresses and point them to a trampoline that jumps to the original call site. However, the important thing to note about these trampolines is that we can store them in execute-only memory, so the attacker can't disclose the real target address. He reads the function pointer, sees only a trampoline address. We can randomize the trampolines independently, so we can permute the order of all the trampolines in the program, and thus the attacker gains no information from a code pointer about the real target of that code pointer. Now, it's important to note that the attacker can still execute these code pointers. We have to allow this because this is the correct functionality for the program. The program needs to be able to dereference and execute a function pointer, but it doesn't need to be able to read the destination of the function pointer in order to do so. We have some extra mitigations to prevent reuse of trampolines as well. So, summing up, we introduce execute-only memory, and we introduce code pointer hiding. How do we do this? Well, we modified the LLVM compiler infrastructure to do three things, really. We needed to separate code from data. So if we embed readable data into code pages, this works on legacy hardware, on legacy x86 hardware, of course, but we need to prevent the compiler from doing this. So we simply make sure that the compiler never emits data into a code page. Easy enough. Then we use the compiler to perform fine-grained randomization. In our implementation, we used function reordering, so we randomized the ordering of the functions in the program. We also perform register allocation and stack save slot randomization. You can find the details for these in the paper. But it's important to note that our techniques are not married to these particular fine-grained code randomizations. We just depend on some fine-grained randomization, and we evaluate it with these. And finally, we implement code pointer hiding in the LLVM compiler. We rewrite all code pointer address assignments. So assignments to code addresses into pointers to instead point to trampolines, these direct jumps. At runtime, we take what we call a redacted program, a redacted application that we compiled using our modified compiler, and we implement execute-only memory and hardware. Now, as I mentioned, we need the extended page table virtualization feature to implement execute-only memory on current Intel systems. To do this, we implemented an extremely thin hypervisor that only enables the EPT feature and sets up an execute-only memory. It simply passes through all other information from the operating system onto the physical hardware. We also wrote a Linux kernel driver to interact with the existing page tables and the extended page tables in order to, when an application requests a page be mapped with execute-only permissions, it actually gets execute-only permissions. We interact fully with legacy applications. If the legacy application was not compiled with our Readactor Compiler, it will request read and execute permissions for its code segment, and we allow this as normal. We also wanted a comprehensive solution. In the beginning, I mentioned that we target browsers. The JIT attack targets browsers. And what do browsers do? Browsers implement JavaScript. All major browser vendors implement JavaScript by using a JIT compiler. What this does is it takes high-level JavaScript code and at runtime generates native machine code to implement this JavaScript semantics. These compilers present some unique challenges when we want to use execute-only memory, since they don't normally emit code. In fact, they usually emit code that's read, write, and execute. So this is a problem. The JIT compiler, in our case V8, assumes mutable code. It needs to be able to change the code frequently. However, we really don't want the code to be mapped as both readable and executable, and we definitely don't want to be mapped writable and executable. So we solve this by actually alternating usage between a mutable mapping and an execute-only mapping. When the JIT compiler needs to treat a page as data, we map it read-write. And when it needs to treat a page as code, we remap it as execute-only. You can see the details in this, for this in the paper. We actually were able to do this very efficiently by actually having two EPT mappings, a legacy mapping that allows read-write, and an execute-only mapping, and we can switch between these two efficiently. You can also see the paper for more details on other challenges that we ran into when implementing JIT support. So we actually modified the V8 JavaScript JIT in Chrome in order to support execute-only memory fully. So of course, as all good system security researchers must do, we need to evaluate the performance of our system. We evaluate on SPEC's CPU 2006, the standard benchmark suite, compute-intensive benchmarks. And this allows us to compare our solution to other competing solutions. But as I mentioned, we want a comprehensive protection. We want something that works in the real world. In order to do this, we need to target a real-world state-of-the-art browser. So what did we do? We took Chrome, we compiled it with our protections, and we defend all of the Chrome browser that many of you are running on your laptops. We simply modified the build system a little bit to use our new special compiler. We then ran it on top of our execute-only environment and protected all of Chromium and its associated V8 JavaScript engine. You can see the paper for more details on this. We evaluate the performance of V8 as well as the performance of Chrome itself. We found the performance to be very similar to that of SPEC, which I will actually show. So for SPEC, we evaluated our performance. And I'll zoom in on the geometric mean here. You can see on the right, the pink bar is our full Readactor system. We incur an overhead of about 6.4% over the unmodified baseline. But it's interesting to note that most of this overhead actually comes from the code pointer hiding component. So on the left in the light blue, we have code pointer hiding, which, to refresh your memory, protects against indirect disclosure, not direct disclosure. And this costs about 4%. So in the middle, in the light green, you can see the performance results for just implementing execute-only memory in hardware on x86. It costs a little over 2%. So in total, our overhead's 6.4%, but a large component of that is our novel protections against indirect disclosure. In conclusion, we've presented Readactor, which is the first completely hardware-enforced execute-only memory protection that you can run on today's x86 processors. We're also the first solution to protect against both direct code disclosure, reading code pages, and indirect code disclosure, reading readable code pointers that gain the attacker information about the code layout. And finally, we are comprehensive. We protect the entire Chrome browser as well as JIT compiled code. Thank you. I welcome any questions.
So what are the attack vectors still left in your architecture?
We don't really handle side channels. So that's an open problem. And I think side channels are a very hard problem, as we saw in previous sessions here. That's a very valid thing. So that would be one thing I would say.
Matthias Peyer, Purdue. Great talk, love it. How would you protect against reusing complete functions as my gadgets that are known to be taken somewhere else in the code where you have to insert these trampolines anyways? And you mentioned something along the lines that you prohibit the reuse of trampolines. Can you elaborate on that?
Sure. We do not prohibit reusing whole functions. However, to reuse a whole function under our system, you first have to disclose a code pointer. So you need to have the code pointer that you want pointing to the function you want to reuse. In many cases, you can do this. We do not protect against this as is. What I mentioned with protecting trampolines is trampolines are not useful for gadgets themselves. So you can get the address of a trampoline, but the trampoline is simply a single instruction, and we randomize that layout to ensure that you cannot reuse a gadget inside that direct jump. But yes, you can still do full function reuse. That's future work.
Thanks. If there are no other questions, you mentioned for the pointer hiding itself has the highest overhead. Yes. Probably for the return instructions where you have to go through the additional indirection. Did you look at other instruction sequences, removing the return instruction and possibly using an indirect jump or something like that?
Very good question. We have not investigated this. My intuition would be that this, on Intel hardware, this would actually be problematic because Intel implements a hidden return address stack so that call-ret pairs are fast. So I actually expect that to be slower than our current solution. We do allow the call-ret stack to function as normal. But yes, you have to do an extra layer of indirection. And it turns out that most of this overhead is actually from the code cache, the instruction cache. We add trampolines. This pollutes the instruction cache, resulting in more instruction cache misses.
Thank you.
Thank the speaker again.